Donc, on a organisé donc une conférence Skype. Et donc, c'était, oui, on a une centaine d'auditeurs qui ont suivi donc, cette conférence. J'espère aujourd'hui qu'il y aura beaucoup plus, donc, puisque c'est à l'échelle donc, arabe qu'on organise donc, cette conférence.
Oui, oui, c'est... en fait, j'ai vu tous les logos et toutes les associations. Je vois que c'est assez large comme invitation. Hein, donc, oui, espérons qu'il y a du monde. J'espère de contenter la majorité au moins.
OK. Donc, bonne chance donc, pour le reste
beaucoup.
de la conférence. Salut Maïssa, comment tu vas?
Oui, ça va, monsieur Nofred. Et vous, comment ça va?
Oui, voilà, donc on est en train de préparer le programme donc, scientifique pour l'année 2021. Hein. J'espère que vous pouvez donc, au niveau de l'association TAIA, de présenter donc, vos propositions en fait pour la collaboration entre l'association et la Cité des sciences.
Oui, bien sûr, ça sera un plaisir. En fait, on a postulé une demande pour un contrat de collaboration avec Madame Dora Rolbe, mais je ne savais pas si la collaboration est déjà faite ou non.
Bon, en fait, vous pouvez donc présenter donc, vos suggestions hein, pour l'année 2021. Hein. Il ne faut pas attendre donc, de signer un contrat. Hein. Donc, puisque vous êtes nos partenaires, en fait. Hein. Donc, ouais. Donc, soyez les bienvenus. Hein.
D'accord. Alors, Paolo, je vois que tu travailles sur Gaïa avec Lisa, avec l'Agence spatiale européenne, c'est vrai?
Pardon, j'avais éteint le micro. Oui, tout à fait. Et je parlerai aussi de Gaïa parce que c'est une mission qui travaille, comme tu sais aussi, surtout pour la galaxie. Mais en fait, c'est aussi un relevé du ciel qui est très important pour les systèmes solaires. Donc, moi, je suis responsable de la réduction des données du système solaire pour le consortium Gaïa. Et là où tu es à Padoue, il y a du monde aussi qui travaille sur Gaïa.
Oui, la comité de Padoue est vraiment très large. Il y a l'INAF, il y a aussi la comité de planétologie au département de la géologie à l'université de Padoue. Oui, la comité est si large. Hein?
Oui, tout à fait.
Alors, comment tu connais David Barato?
Bah, écoute, je ne sais plus quand je l'ai connu la première fois, mais j'en ai entendu parler parce qu'il est planétologue aussi. Donc, j'ai assisté à quelques séminaires et il est venu ici à Nice faire un séminaire sur son initiative de collaboration entre la France et les pays africains en astrophysique. Et du coup, je me suis intéressé un peu à ce qu'ils font et aux possibles applications de cette collaboration pour faire de la science ensemble. Donc, bon, c'est intéressant. Et toi, tu l'as connu comment?
En fait, j'ai connu depuis 2015 quand j'ai cherché l'opportunité de faire un master à Toulouse à l'IRAP et depuis pour une thèse. Alors, je te connais de cette point-là parce que je l'ai contacté quand il travaillait à l'IRAP. Je demandais la possibilité de faire un stage là-bas avec Sylvestre Maurice. Et de Sylvestre Maurice, j'ai connu David Barato.
D'accord. Bon, très bien. La semaine dernière, ils étaient au Sénégal. Pour observer une occultation, tu as suivi peut-être la chose, pour observer l'occultation d'une étoile par un astéroïde. Et ils étaient au Sénégal, il y avait aussi 2 collègues ici de Nice. Et moi, j'ai renoncé à y aller, bon, parce que en ce moment, avec les voyages, c'est un peu compliqué, avec le Covid et tout, mais j'espère pouvoir collaborer encore et faire de ce genre de choses, moi aussi, bientôt.
Ok, ce qu'on va faire, Paolo, je vais commencer par vous présenter une ou 2 minutes. Après, je te donne la parole et tu peux commencer après votre présentation. Ça va?
Pas de problème, parfait. Quand tu veux. Là, il est quelle heure? 14 heures juste maintenant? Oui.
Oui. Okay, should we start?
Seulement une question, je garde la caméra allumée ou c'est mieux que je la éteins après?
Comme vous voulez, si tu es confortable, tu peux laisser la caméra ouverte, sinon c'est comme vous voulez.
Bon.
So, hi everyone, and welcome to our participant here in Zoom meeting. And today we have another session from AstroTalk, and our guest today is Paolo Tanga. With Paolo is astronomer based in the Observatoire de la Côte d'Azur in France, and where he is moving after that work and years in the Observatory of Italy. And his main scientific interests are in the area of formation and evolution of planetary system. He is a member of the Solar System Planetary and Simulation Working Group. Paolo also has contributed in the simulation of light curves of asteroid to plan testing of data and version procedure, and also the study of the observability of the natural satellite of the solar system. He loves hiking in the Alps and also observing the night sky. From his background, to know more about Paolo, and his presentation for today, you can join us for this meeting. So I would like to thank all our participants today. We're gonna have an amazing talk about asteroid from space to the ground. So Paolo, we can start.
Okay, thank you. Hi everybody, and thank you for coming to listen my presentation today. So just on a technical side, I think to save some bandwidth, I will switch off my video. You will have to focus on the slides. Sorry for that, but just to be safe, I think it's better on my side to do this. So what I will present you today is a rather broad landscape of what asteroid science is in practice today. So this is intended to target people that are not only researchers, but also amateur astronomers of passionate in astronomy at all levels. So I will not be too technical, I hope. And okay, so just to sit comfortably and we can start. You probably all heard in the past about asteroids, and you know that asteroids are mostly situated in a belt between the orbit of Mars and the orbit of Jupiter. So I hope you see my mouse cursor on the screen so that I can indicate what I'm talking about. So all the green dots here represent the space field by what is called the main belt of asteroids. And then you have other categories of objects that are farther away to the orbit of Jupiter, such as the Trojan clouds. These are asteroids that are in equilibrium points at the distance of Jupiter, the blue dots here. And in the center, the red dots represent basically what is coming toward the orbits of the Earth planets, the telluric planets, which are crossed by the so-called Earth-crossing asteroids. Okay, there is a huge variety of small bodies. Now, the moon probably formed with an impact with the Earth, so we can put a little bit that aside, but looking at the other objects, starting from Pluto down to Ceres, Vesta, and the smaller asteroids, we cover all the possible scales. Now, if I had to draw the smallest minor bodies on this slide, you couldn't even see them, because we go down to scales of meters or centimeters, depending upon where you stop to classify them as asteroids, and they become objects. Starting from Pluto down to Ceres, Vesta, and the smaller asteroids, we cover all the possible scales. Now, if I had to draw the smallest minor bodies on this slide, the microphone that is not muted, you couldn't even see them because we go down to scales of meters or centimeters, depending upon where you stop to classify them as asteroids, and they become objects. Okay, I think there was a mic that was not muted, so there was an echo. Sorry for that. And I think I continue from here. Okay, so this variety of sizes here is illustrated in comparison to Italy. Sorry for that, I just choose my country, but just to give you an idea. The largest objects in this category are kind of small planets on their own. So they present a variety of features, of surface activities, such as those discovered on OSIRIS by the Dawn mission. And already seen before by the Hubble Space Telescope, you see these bright dots that are probably what is visible of kind of hydration, abundant hydration of the mantle that comes to the surface under the form of salty deposits that have a very, very high albedo, so a very, very high reflectivity of the light. But you heard about asteroids in certainly for many different reasons, probably because they can be dangerous, so they can strike the Earth and provoke regional or global damage, so we should take care about this problem. They could even be the target of manned space missions for astronauts that go there to explore these objects, or even for asteroid mining. As you can see here, with a suitable spacecraft, you could think to send space miners and dig asteroids to extract some metals and precious materials. So certainly you heard talking about all these aspects, but what I would like to stress here is that in fact, in order to do all these wonderful things with asteroids, we have to know them better. The first asteroid was discovered in 1801, 1st of January, by Giuseppe Piazzi, an astronomer in Palermo in Sicily. And this was OSIRIS, the largest one. And how he discovered this object simply by looking at the stars, and he saw a star that was moving with respect to the others. This is the way we discover asteroids today. It has not changed much. So here you have an image taken by an amateur telescope of 35 centimeters, and it's a small asteroid that is crossing the field of view, and over several exposures you see that its position is changing. So in this respect, nothing has changed between the first discovery and today, in concerning the method of which we detect the presence of new asteroids. But of course, the efficiency of this process has increased much. And you can consider this sequence of discoveries basically for the first 50 years, there were just nearly 40 asteroids discovered. And then in the next 50 years till 1900, the number was multiplied by a factor 10, and so on. The discoveries went on till today, where we are we have about 1 million objects known. So this table was updated on July 6th and shows you, well, today there will be a little bit more, but let's say we are close to 1 million total objects here. And this is a table extracted from the Minor Planet Center, which is an institute of the Harvard University in Cambridge, Massachusetts, that is officially charged by the International Astronomical Union to collect the observations of minor planets, to name them, to give them identification codes, and compute their orbits in such a way that their identity is preserved. And you can see here At that day, there were about 250 million measurements of asteroids, meaning for that the measurement is a position and the brightness of a minor planet has been observed from the first one discovered to today. So we think that the minor planets are important for several reasons, but let's, as I showed you, we are dreaming of going to them, to mine them, extract materials, etc. But let's think from the scientist perspective. Minor planets are mostly important due to their relevance for solar system formation and evolution. If we believe, we have been believing for a long time, that if we are able to explain how the asteroid belt formed and how it evolved, we will understand the evolution of the solar system. Basically, we think that the asteroid is the remnant of the process that from the early protoplanetary nebula led to the formation of large planetesimals and then the planets. So between Mars and Jupiter, the situation was dynamically too unstable to form a big planet, and several of the bricks remained in this kind of small size, and then went through a complex evolution that I will just sketch for you in a few minutes. So now let's imagine this scenario in which you form a planet. So basically, till I would say 15, 20 years ago, we had a rather quiet view of how this was formed. After the disk was formed, everything should have gone smoothly by growing larger and larger dust grains till the sides of the planets, and the big objects that were capable of colliding each other and grow till the object we observe today. But in fact, the situation has probably been much more chaotic. So if you want to understand where the asteroids come from, one has to take into account that this chaos is occurring. I show you an example of what I mean by that. And this was derived in a planetary formation model that was developed here in this observatory. So it's called like the NIS model for that. And you can see here a simulation that shows the orbit of several objects that are beyond the orbit of the farthest planet at the beginning of solar system formation. I just stop a second here to let you notice that here I just have the orbits of the outer planets from Jupiter to Uranus. Oh, that's strange. You see, Uranus and Neptune are not in the same position as today. They are inverted. And this is quite compact with respect to the solar system that we observe today. In fact, this configuration is a kind of special because it explains some compositional differences between Neptune and Uranus, so they justify this inversion. But also dynamically, you will see that the interaction of this closed system can then become unstable and lead to the situation of the solar system as we know it today. So just wait for about 800 million years, and of course we will see this in seconds, and you will see a big giant instability occurring with the planets jumping to their current position, and all this belt of external objects that are spread all around. We are nearly there. Hop, okay, this is what's happening. So the orbits of the planet then stabilize to a completely different situation in which all the small bodies were scattered around, and due to this instability now, Neptune and Uranus have been inverted and are in their current position. Is this true? Is this correct or not? So hard to say without looking at the details. So when we look now at the asteroids which are in the inner solar system, do they bring the signature of these chaotic beginnings? Okay. If this is the case, it means that what we observe at the distance of the asteroids, so around here, between 2 or 3 times the distance of the Earth from the sun, so 2-3 astronomical units, is the result of a huge mix that occurred during the large instabilities and the troubled history of the solar system. And probably here we see what has been brought from other distances during these chaotic phases, either as objects that formed in the outer solar system where the ices were more abundant, or objects that form in the inner part where the solar system is hotter and are more abundant in rocks. So if there is something remaining here, it's probably not really what is what originally was in this location, but it's something that is being mixed and transported across very large distances in the system. So if you want to sketch what probably happened, is that from an accretion disk here at time 0, stretching from the sun to the outer planets and the TNO, the Kuiper belt outside, you had a gradient of composition from the rocky bodies in the center to the icy in the external part. And then there was this big instability phases that I don't detail here, but basically that mixed all the blue and the red dots together and created a mix of material in the solar system, with also the big planets that migrated and adjusted their position based on the mutual dynamical perturbations. So what happens today is, it's on the bottom row here, is that we observe in the main belt this mix of blue and red dots that bring some memories of what was the original compositional gradient, the different in composition across the distances in the solar system. But it is a very, very mixed and has had a very complex history. Now, what is collected here did not only evolve through these chaotic transportations across the solar system, but also through other mechanisms. One for all of them are collisions. Once you have a dense asteroid belt, you have to imagine that at the beginning of its evolution, there were big mutual collisions among these objects at a rate which is much higher than today, because probably dynamical perturbations and collisions eroded the belt, and today we observe less than 1% of its original mass. So we had big collisions creating fragments, and these fragments that are here shown to fly away, in fact, they go away from the orbit of the original, what we call their parent body, but these sons and daughters here probably are not so far, in fact, in terms of an orbit. So all these fragments that were created share about the same location in terms of orbital elements, of orbit geometry, and are known today as asteroid families. So if this is true, if this evolution happened this way, our numerical simulations show that in fact many of these remnants probably are clusters of fragments. And in fact, there were people that suspected this for a long time. One of them is Donald Duck and his Uncle Scrooge, because you see here already in 1960, Carl Barks, who was one of the major Disney cartoonists, drew this story in which Donald jumps on an asteroid which is so fluffy that in fact it goes through. And so the fragments are not even glued together, so they're simply held together by gravity, no cohesion. And Uncle Scrooge is glad he didn't try to store some money there. So you can see, of course, this is for the funny story, but in fact, this drawing was probably not far from what we know today of many small objects. So where do we look for these asteroid families, these fragments that are created from big collisions? So we look for them, of course, where we have more objects in the main asteroid belt, and they appear as clusters. So just forgive me for this detailed plot, but here each dot represents the orbit of an object. And you can see here the orbit are plotted as a function of what is called the semi-major axis. Basically, roughly speaking, we can imagine this as the average distance of the object from the sun and its inclination. So you have high inclination orbits, low inclination orbits, and you can see that the distribution is not uniform. It's cut by dark bands where you have no asteroids. Basically, these are the zones that are unstable. So the asteroids out there would be perturbed by Jupiter mainly, or Jupiter and Saturn, and would drift away. So these zones are empty. But you also see that there are many, many clusters. Now, these clusters here are colored in terms of albedo. So brighter asteroids are redder in this scale. You can see that away from the sun, the asteroids are mainly dark, and toward the sun, they reflect more light. But what you can see also is that you have blue and red clusters everywhere. So these are probably the remnants of what we call dynamical families. And this family of dots disperse gradually over time in such a way that after a billion years, probably some of them are so dispersed, so sparse, that you cannot even identify them any longer. Some of them are rather compact. Oh, sorry. Some of them are rather compact, so maybe you can imagine that these collisions occurred more recently. So is this spread a way to understand evolution? Of course, because if we say that more compact means younger, we can analyze the mechanism that induces the spread, the speed of the spread, and derive the age of these clusters. So which is the clock that we can use? It is called Yarkovsky effect. Okay, it's don't be scared about this strange name. In fact, it's quite simple. It's like when you shoot with a gun, a projectile, and you have a recoil. Now the asteroid is not shooting projectiles, it's shooting photons. So it's shooting light that comes out as a thermal radiation because it is warmed up by the sun, and it re-emits his thermal radiation, his heat, under the form of radiation. So this re-emission, depending upon the spin of the asteroids, if it rotates in one direction or another, makes the asteroid orbit drift. And the smaller the asteroid is, the faster is the drift. So gradually, this drift induces a dispersion in objects that were close together and that gradually spread and cover larger and larger space around their orbits. So we can draft a story of these asteroid families today, starting from the main belt. It is depicted here in colors around the sun. You had collisions that created fragments. Each one of these objects is probably a Rubble pile, so composed by smaller fragments, but these are small enough to feel the effect of the Yarkovsky force, so they disperse, and some of them encounters instability regions perturbed by the planets that inject them into routes, into paths that lead them to reach the inner solar system, and they are detected as near-Earth objects or hazardous asteroids, etc. So they become, for instance, objects of different categories among those that cross the orbit of the Earth, such as the Athens, the Apollo, the Amor, depending upon their orbital properties. There are several categories, but let's say the morality of this is that these objects, these small asteroids that are sometimes called dangerous, in fact, come all from the main belt and from rather recent collisions, and they took one path, one dynamical path that injected them towards the end of the inner solar system, where they cross the orbits of the Earth, or sometimes also Mars and Venus, and so they are very perturbed, and their lifetime in this region is quite short. But sometimes they fall on the ground, of course, and we have interesting scars that remain on the surface of the Earth and show that, in fact, we were bombarded as the moon was. Simply the activity of our Earth crust and the erosion by the atmosphere changed the signature and deleted many craters. But of course, you can see that all of these dots represent a crater detected on the Earth. There are many of them, and we can still go in place and study them as if we were on the moon, in places where they have not been eroded much. So here you can see a few examples. So this is a Wolf Creek crater in Australia, which is about 1 kilometer crater, and it was probably impacted by a 50,000 ton asteroid 300,000 years ago. Here is another famous example, meteor crater in Arizona, younger crater. Here is a crater filled with water in South Africa, very spectacular, and so on. So if we want to understand which is the risk now to have a big asteroid impacting the Earth, of course, the way to go is to try to have a complete census, a complete catalog of all the objects that can cross the orbit of the Earth. And basically today, we can say that we are nearly complete at about 1 kilometer scale. But if we go to smaller asteroids, we are less and less complete. And the most dangerous for us among these bodies are those that are maybe a few hundred meters across or less, because they are the most numerous, and also they are difficult to detect because they are fainter when they are far from the Earth. So they become detectable only when they are very close. Okay, so depending upon the size of the asteroid, you can have a different energy of the impact on the ground. So in this plot shows you the frequency of occurrence of an impact going from a scale of 1 year to 100 million years, and on average, which is the power of the explosion that you can have from such an impact as a function of the frequency. So an event creating the meteor crater probably occurs only around every few thousand years, and other events are even more rare. But that doesn't mean that they're not dangerous. Even if the asteroid is smaller, the frequency can become high enough to be of a potential concern. So there were scales of danger that were derived depending upon the scale of the damage that an asteroid could cause. I don't go into details here because it becomes very technical, but basically you range from objects that are a few tens of meters across and then they explode in the atmosphere that make no significant ground damage, to regional damage with craters that are maybe 1 or 2 kilometers across, but that are much more rare. And then, of course, the biggest impacts, creating extinction and so on, are very rare. We are in terms of intervals, we are around several tens of million years. Okay. The Torino scale was a scale that was built to classify the danger of an impact depending upon the damage it can create and the collision probability. So when you hear about an asteroid, is this scale to assess how much dangerous it is. But up to now, we have no objects that go beyond grade 1, so it needs to be monitored carefully to see if its orbit can become dangerous. We have never discovered something that was really very dangerous up to now. So let's look at this problem of impact danger the other way around. So which are the probabilities? Let me do this exercise, which is kind of strange, but which are the probability to die from rare events. So if you unfortunately, we know that everybody must die, but let's look at this as starting from the things that are very, very rare to happen. So I'm sorry for English speakers, this is in French, but I will explain that. So, which is the probability to die for the fall of a coconut from a tree? It seems that there are kind of 150 accidents like this per year. So it's not completely negligible, but of course, if you average that over the whole population of the Earth, given that this kind of trees is not everywhere, you get this probability of 1/250 millions. So it's very, very difficult that this can happen. So which is the probability to win the first prize of the biggest European lottery, at least the one that is available in France? You are at these numbers of the same order of magnitude, which is the probability of dying by falling from the bed. So I didn't know that, but it seems it happens. So be careful. It is 1/2 million anyway. It's quite rare. And then, which is the probability of being killed by a thunderstroke strike? It's 1/80,000. Or dying in a plane accidents, even smaller, or a circulation accident, and so on. And if you look at the asteroid, it is to die due to the impact of the asteroid 1/1 million. So can we say that it is high enough to be a huge concern? I don't think so, but still, it's halfway. Let's say it enters in the domain of rare events, but not impossible, because the problem is that it is very rare, but when it happens, of course, it can have a big effect on a large number of persons all of a sudden. Now, I don't want to go through much details here, but just want to show you this picture that is, let's say, illustrates the small end of the size distribution when you look at the meteors in the sky, and you can see them falling during, for instance, summer nights. So now, these are not dangerous because they burn completely in the atmosphere. But in some cases, there are big chunks that are not only of cometary origin, but that are more solid, and they can enter the atmosphere and make some effect. And I think a very good example was the Chelyabinsk fall, which occurred on February 15, 2013. So this one is especially interesting. Why? Because especially interesting to me as an example, because in fact this was not such a large body, and his cohesion was quite small. So in fact it disintegrated in the atmosphere, and only small pieces fell to the ground. But okay, let's have a look to how it was seen from cameras running on the cars that were driving around the region where it fell. Okay, it's quite impressive, the flash, of course, and you can see here several other videos showing just the light that came with these objects. It was very early in the morning, as this region where the sky was still a little bit dark, and you can see when the asteroid makes this flash in the atmosphere, everything lights up as if it was midday. So what was somehow surprising is that in fact the damage occurred due to this asteroid, and this was mainly due not to the impact of the fragments, which were, as I said, they were small, but to the shock wave of the explosion in the atmosphere that created most of the injuries on people, because the shock wave arrived about 30 seconds after. So people were able to go to the windows, see what was happening, go on the roads outside, and then they were invested by broken glasses and debris that were dispersed by the shock wave when it went down and was hitting buildings and windows, etc. So the damage here was not direct from the stone that fell on the head of people, but from the shock wave it injured several. So this was quite a lesson from that point of view, that sometimes there are aspects of the asteroid impact that are not properly taken into account. Okay, I will move on with this. Yeah, you see here what we can call the crater of one of those fragments fell in an icy lake nearby the city of the town of Chelyabinsk, and created a hole in the ground. And here I have just one example of direct damage of a fragment, the heat factor in the area, and so on. And then the trajectory of the object when it was in space, as it was derived from the observation of its entrance in the atmosphere. Interestingly enough, this object was also imaged by meteorological satellites that saw the streak of smoke created by the object while going down in the atmosphere. Here is the terminator. So on one side it is night, and the other is daytime. We are above the town of Chelyabinsk here, and you can see this stripe that was basically left by the asteroid crossing the atmosphere. Okay, so now, of course, this when an object like this enters the atmospheres, and it is so fast that nothing can be done. So the whole, let's say, the whole goal of discovering potentially hazardous asteroids is try to discover them when they are still up in the sky. And let's say we can identify one milestone in history by thinking at this asteroid which was discovered in 2008. So it was called 2008 TC3. And here is an image of the object while it was in space. And it was clear that the object was going to hit the Earth pretty quickly. It was identified that this was on Earth in a trajectory that was colliding with the Earth over, let's say, a few days after its discovery. So it was also clear that it was quite small, so that it would not make a big damage. And then the fall area was identified in this region in Africa, where then people went to search for fragments, because in fact the bolide was seen, this bright track in the sky was seen. There was some witness of the fall, and then the area was computed where the fragments could be on the ground, and the people were dispatched to look along this track for places where the fragments could be. And in fact, here you have different fragments that were collected, and they were dispersed along this direction. You can see here, as there was a desertic region, it was quite easy to distinguish these black rocks on the background of the bright sand, and find them back take them for analysis. Okay, what you know maybe is that in France there is also an interesting network of sky survey that is based on all sky cameras that try to detect all very bright bolide that cross the sky, and then determine their trajectory in such a way that from their trajectory one can try to find potential fragments that reach the ground soon after having appeared as bolides in the sky. So why we are so interested to collect these fragments? So if you are a planetologist, you certainly know, but if you are not, maybe you miss this connection between what we collect on the ground, so these meteorites, these fragments that come from the sky, and the asteroids, because basically these fragments here that can have different mineralogic compositions are pieces of asteroid that we can really touch. So asteroids are among the very few celestial objects, maybe the only celestial objects that we can not only observe from a distance, but also touch with our hands. Sometimes it's difficult. Certain categories probably we cannot touch because they disintegrate in the atmospheres. But if the minerals are strong enough to survive the entrance in the atmosphere, we can collect pieces on the ground. So you can see here different kind of meteorites. This one on the upper right is quite spectacular because when it is cut, there are transparent inclusions, glassy inclusions in the melt that is quite heterogeneous. At the bottom right, you have an example of a kind of pristine material in which you have a dark matrix and a very light inclusions inside. On the left, you have examples of metallic meteorites made by iron. This is pure iron with some crystals inside, a form that is not found on Earth. It is formed only in the core of differentiated large planetesimals. Okay, so the connection between meteorites and space. There are some famous falls dating back from the 19th century and older. But anyway, it's very, very important because, of course, if we understand what created the material composing the meteorites, we can understand also how the asteroids evolved. And asteroids, we know, have a large variety of shapes and surface compositions and structures, everything. Here I show you a quick overview of asteroids that have been visited by space probes. So this was already a few years ago, ranging from the Matilda, which is 60 kilometers in size, and Ida, again 60 kilometers in the longest direction, to the smallest ones visited by space probes that are only a few hundred meters across, and are mainly near-Earth asteroids here, except for the biggest ones. Eros is the first discovered near-Earth asteroids up there, and you can see all of them are covered by craters. And here on the bottom right, you have some cometary nuclei, kind of a little different category because these are active surfaces that release gas and dust. So I don't speak much about them today. But let's have a look in detail, for instance, to the small one here, Itokawa, okay, which was visited by a Japanese mission a few years ago, and shows with very, very highly detailed, high-resolution images of its surface. So you can see how irregular it is, not only the shape, which is kind of banana-like, but also the nature of the surface is very different if you consider the tips or the intermediate parts where it is so smooth and covered with dust or small grains. In fact, what is surprising is that there is very little dust. These are mainly small grains like those you see here, pebbles, that goes down in this image to a few centimeters. And really it gives you the impression of what a rubble pile could be. So how many little pieces could compose an object like this? Now, the point is that, of course, as always, we only see the surface of these guys. We don't see what's inside. And so there is very little information on internal structures. What is creating this overall strange shape? Are just two big blocks together covered by small blocks, or there is something else, or simply it's just a conglomerate of very, very small blocks like those that you see on the surface and that are shaped like this. Very, very difficult to say, and no clear answers today. Now, the most recent visited asteroids by space probes are Bennu and Ryugu. You heard about them, probably will hear more in the coming months and years, because they are visited by probes that are devoted to take samples on their surface and bring them back to Earth. So they are about the same size, few hundred meters across. You can see their shape is quite similar. Their spectral type is a little bit different, meaning that the surface composition is a little different between them. And you can also see the traces of shallow craters that are not so sharp as when you look at the big craters on the moon, but are created in a small gravity environment, and probably they've been eroded by some mechanism. So this is how it looks like, the Hayabusa 2 mission, in which my laboratory is also participating, and it is going to pick up samples from such asteroids. Just to give you some highlights, there was some months ago the burn that is going to bring back the samples to the Earth. But let me go quickly on this part. I will show you some movie of Ryugu as it's rotating. You can see large blocks at the poles, smaller blocks, a kind of ridge or bulge at the equator that gives this strange geometry. It is not circular. It's clearly inflated at the equator. And it probably comes from the mechanism that due to rotation of the object and the small cohesion of the surface are capable of displacing material on its surface and accumulate it in a certain region of the body. Okay, so this is how Ryugu would look like if it was in Paris, in the Champ de Mars area with the Tour Eiffel there. Some close-ups of the surface, and just a sketch to show how now we are starting to try to write the history of the surface of these objects, from when it was created by a catastrophic disruption. It came out as a rubble pile, and then it was cooked by solar radiation, becoming red. So this kind of aging, what is called space weathering, that changes the age of the surface and turns the color to reddish. But then the displacement of small pebbles on the surface uncovered pristine material around the equator that we can still observe today, and this superposed to the activity that of impact that created some craters. So by this space mission, we are really trying to target specific objects and write their history to understand how they form, starting from the early impact that created them. Okay, let me skip some details about how this space probe work, just to give you a nice movie of the Hayabusa sample collection that shows you from a camera, from the point of view of a camera of the spacecraft, the moment in which it touches the surface of Ryugu and goes away with the sample collector that takes some of the small fragments that you see flying around after the touchdown. Okay. There were also, during this mission is fascinating, it also released some very small satellites, what we call nanosats or CubeSats, that went on the surface of the object and took a snapshot. Here you see the reflection of the sun. Basically, this is kind of sunset observed from directly from the surface of an asteroid. You see very small stones close to where this camera fell. Okay, another mission you will hear about much is OSIRIS-REX, which is mainly driven by NASA with some international collaborators, and this is exploring Bennu. And you can see here that Bennu is quite peculiar. What has been discovered is that the surface of Bennu releases small pebbles and stones. You can see this sparkling speck of dust there in this image that show up because they are sunlit and they follow some trajectories around the object, and then they probably fall again on the object itself. So there is some activity on Bennu that spits out some fragments from time to time. Some of them probably escape even around its orbit and don't fall back on the object. And it's an interesting story because several mechanisms are now being investigated about how this can originate. But you have to understand that the gravity on the surface of this object is so small that it's very small perturbations are sufficient to create this dust escape. This is the place on Bennu at high resolution where OSIRIS-REX is going to take its samples. And the point is that, unfortunately, it was expected to have much more dust. But what you observe here is basically small stones. So the sample collecting becomes critical, and they target really places where the surface is smooth and where dust is probably more abundant. So you can see here a scale of, this is about the size of a house, a small house, okay? So the sample collection, there was already a first touch and go sample collection on August 25, but in a few days it will probably follow the operation directly streaming on the web of about the second sample collection just on October 20 coming soon. And then these space probe will leave Bennu at mid-2021 and come back to Earth 2 years later. So in 2023, we have pieces of this asteroid taken directly from its surface coming back to us. Okay, so now as I see that I'm coming to the last 10 minutes of my conference, let me give you some takeaway message that is more general about what we would like to know about asteroid, in fact, because many things are not yet known. So just to give you an idea, let's visualize some statistics. Here we have the Sun and the Earth. Okay, let me plot all the known asteroids, about all the known asteroids, and they come out as this big asteroid belt. Reaching here, we look at the main belt mainly, so we stop at about 3 astronomical units from the Sun. Okay, the space seems to be filled with the small minor planets. Now, let's imagine we want to understand better this population in general. We cannot just be happy with a handful of objects visited by space probe. We need to have properties for a large number of them. Otherwise, it's like being in a forest, just pick up 3 or 4 grass leaves and try to understand how the forest was formed and how it will evolve just by looking at a couple of samples that were collected. No, we want to know more. We want to look at all the trees and classify them, see how many varieties we have in this forest, and so on. So let's start from, for instance, for how many objects we know a size, even an approximate one, and throw away all the others for which we don't know a size. So we drop from 1 million to about 140,000, which is already kind of a sample. It is very helpful, but many of these sizes one has to know are quite approximate and prone to error. So we can say probably we had 100,000 reliable sizes, okay? Now, if you want to be strict enough and say you want only the most accurate, this probably goes down to 4,000. So the population diminishes even more. Now, okay, we know how big they are. Let's see, do we know how fast they rotate? So probably the rotation period is known for a few thousand asteroids now. And so this population of known properties decreases even more. So if we go to 5,000 rotational periods known. So you see, we started from a very, very populated region, and we understand now that just a small, tiny percentage of that has physical properties that are known. So for how many of them we know the composition? We go down to probably 2,500. That's about the order of magnitude. Okay, still, we start now to have problem. We are trying to understand the whole evolution of the composition of these objects, how they travel the solar system and blah, 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 all what I said, by just looking at a very, very small fraction. And now we talked about sizes, and what about asteroid masses? This is a whole tricky story, because to weight an asteroid, you need to measure its perturbation with respect to other bodies. It's very, very difficult. So we can say probably we have 20 or 40 quite well-known masses of the biggest asteroids with reasonable error bars and values that are consistent with each other. So you see, basically we know nothing about the whole statistics of this population. So we need to apply observational techniques and rely on new surveys to provide us with information. So let me skip a couple of slides of how this can be done to collect this information, but let me go to something on which I work directly. Okay, and then we come back on a few elements. So surveys that provide us information about asteroids. So I'm talking a little bit, spending a few minutes on the Gaia mission, which is a space telescope which is placed at a certain distance from the Earth in a very stable environment. It has two telescopes on board, and this was built mainly to study the stars and the galaxy. But in fact, given the fact that it is a kind of fundamental astrometry mission, which measures very, very accurate positions in the sky and the colors, the spectra of many, many objects, 2 billion stars, in fact, it gives such a rich return in terms of science that it can impact all disciplines, from relativity testing to the physics of double stars, stellar populations, the galactic dynamics, and so on. And those are the solar system. Now, how we mentioned, Gaia is built by two telescopes that are contained in this cylinder up there, and they image the sky in two directions that are fixed at a certain angle apart, and the imaging device is a big CCD camera, which is about 1 meter in size, one of the biggest ones due to space. Now, this Gaia mission, you probably already heard about that. If not, look for some documentation. There are very, very interesting videos about what Gaia is producing. And one can compare it to the biggest telescopes that are on Earth. You can see a whole family here, from the 10 meters, Subaru and Gemini, up to telescopes that are planned. Here it is written 2022, but this is an old slide. You have to think that these telescopes are not really yet built, but the extremely large telescopes, several tens of meters across, Giant Magellan telescope. You see, these are very, very large mirrors that go very deep to look for very faint objects in the sky. And Gaia is just a tiny mirror here in the left. So one can say that this very small telescope there, but is very specialized to provide very precise measurements, is really bringing a revolution to our knowledge of the sky. And you can immediately understand that by looking at a single slide that traces back the history of our knowledge of the sky over time, starting from very ancient times, 100 years before Christ up to now. You can see how the accuracy of the positioning of the stars increased over time from one observer to the other. Basically, all these observers here till Alexander were observing the sky at the telescope or by instruments that anyway were driven directly by the astronomer and its own eye. Then the photographic plates and the CCD cameras came, and then it came the epoch of the space missions. So Hipparchus and Gaia performing space astrometry, and you can see the trend of improvement made a big jump over the last, let's say, 30, 40 years. First with Hipparchus, and then in 2018 with Gaia, this second data release, bringing the errors in position very, very low, and permitting to access a whole category of astrophysical phenomena that was not possible to detect before. So Gaia was launched in December 2013. It went about 1.5 million kilometers from the Earth, away from the Sun, which is called the Lagrangian point L2. And in 2018, it released a very complete catalog of the sky with 1.5 billion stars observed, many of them with their own parallax and proper motion, with their color, so to know their composition, etc. And the small dot on the left here is the 15,000 solar system objects that were in this data released by Gaia. So these are the numbers. This is a plot of orbits of asteroids that were contained in this data release. And if you go on the web, you also find animations and even software tools like this one, which is called the Gaia Sky, that allows you to, if you download it, it allows to plot all the catalog of Gaia stars, to plot the orbit of the asteroids observed by Gaia, and even use virtual reality devices to visualize them in 3D. It's very, very funny tool, which is very impressive. So now, why this represents a revolution for the asteroid studies? You have to understand that most of the measurements at Minor Planet Center, the numbers that I showed before, are not very precise. They are about half an arc second in precision. So this is a 500 milli-arc second, okay? Now Gaia arrives and immediately goes at the precision of the best, or even better, at about 1 milli-arc second with 2 million observations in 2018. So there is a jump of 400 or 500 times better than what we had before. And this brings a consequence, because of course, I mentioned about the dispersion of asteroid families due to the Yarkovsky effect. Now, if we can measure orbits with more accuracy, when you go toward asteroids that are smaller, here there is a group of asteroids which is the Arigone family. The largest member is there, is big, and it's this position, this distance from the Sun. But you can see all the other members dispersed by effect of the Yarkovsky effect. So if you can measure the orbits better, you can put a better age on these families and better understand the evolution of the solar system. So unfortunately, I have not much time to give you more details. So let me just give you another direct consequence of Gaia, which is the observation of stellar occultations. This is particularly important. I know that among you there are amateur astronomers, and some of you are invested in using small telescope to do useful things. And one of these useful things is to record an asteroid that hides a star. And this can be done by network of telescopes that observe at the same time the same star, but are placed in different positions on Earth. So each of them will see the asteroid being occulted by a different part of an asteroid. And when you collect the information of this occultation, you can build, for instance, a shape, a silhouette of the asteroid that's projected on the sky at the moment of the occultation. So what the occultation is, typically the observation consists in observing a star. Maybe you don't even see an asteroid, that for a few seconds is hidden by an asteroid due to its motion passing on the star. And so you go from the observation of constant luminosity to the occultation itself, a few seconds, only a few seconds of occultation, and then you recover the brightness of the star before the occultation. So this is what you observe, and then what you get is a very precise asteroid position relative to the star, and with several chords, you can also get a shape. So you have many applications of this technique. You see here the observation of several occultation chords. So basically what happens there is that each line corresponds to a different observer, a different telescope positioning with respect to a double asteroid, which is Antiope. So you have here the two components of the asteroid, and you can see that by putting together all the disappearance and the reappearance of the star, you really trace the shape of the two components of this system. Other occultations have been used to discover the rings around the trans-Neptunian objects, or to measure the gradual dimming and brightening of the star behind the atmosphere of Pluto, and measure the density of the atmosphere of Pluto from the ground, which is pretty impressive. Now, there was a big step that, thanks to Gaia, occurred last year in 2019, because up to now it was practically impossible to predict occultations by very small asteroids, such as, for instance, near-Earth objects that are so much interest to us. But in 2019, predictions for Phaeton, which is only 6 kilometers across, were successful. So it was possible, even from our region here, close to Nice, to position a 1 meter telescope. We took one portable 1 meter telescope, which is a pretty big instrument to move, but we have placed it in this blue corridor where the shadow of the asteroid projected by the star was expected to be. And in fact, we were able to observe, this is the light curve, and this is the flux draw. We are able to observe the dimming of the star due to the occultation for only 2/200ths of a second. Sorry, 2/10ths of a second. Here is an enlargement of that. So it was very fast event, but it gives you a very accurate position, because as you know, at the moment of the occultation, the asteroid and the star are superposed. So if you have the position of the star observed by Gaia, you can tell very accurately where the asteroid is and better study its dynamical properties. Then if you have several chords, you can fit a shape to that. Now here were only 3 in the case that we observed, but it was already a success for such a small object. So I will finish with the very last travel to far away in the solar system, where you have other small objects that are beyond the orbit of Pluto and Neptune. That's called trans-Neptunian or Kuiper belt asteroid. One of them was visited by the New Horizons mission, and again, this object appears to be very small. It's only 30 kilometers across, but when you put it at 50 astronomical units, so very far, it is very small seen from the Earth. And the idea was that in order to allow the New Horizons mission to properly target it, it was needed to observe stellar occultations. And so its orbit was improved thanks to Gaia, stellar astrometry, and it was possible, in fact, to observe occultations of it. And the press, of course, was highlighting this collaboration between different missions, Hubble Space Telescope, Gaia mission, and New Horizons, across say, big international effort for targeting these objects. You probably saw in the press images of Côte at the time of the close encounter of the mission, but not all of you know that probably that in order to obtain these images, Gaia and the occultations were seminal, because basically what happens is that the asteroid is the target was to pass about 3,000 kilometers from the object with the New Horizons mission. So the target was there, and all the operations at the distance are done in full automatic mode. So the satellite, the probe, had to know exactly in which direction the camera had to be pointed to be able to frame the object in the field of view. And so it was needed to have a very accurate knowledge of the distance, the exact moment at which the asteroid was closest to point it. And these were all this while traveling at a very high velocity, 25,000 kilometers per hour. So a very difficult task. And this was solved thanks to this cooperation between the space missions. So you see, studying the asteroids has many aspects, and it's not only space probe going on site, it's also a matter of knowing better statistically their properties, targeting them by large surveys that can have an impact on the way we approach their study from the ground and from space. One of the biggest surveys to come is the Vera Rubin telescope, also called LSST, which is a large telescope producing about 200,000 images per year, covering the whole sky very quickly in very big depth, and is going to discover millions of new asteroids very, very quickly, and also measuring their colors in such a way that their composition can be inferred. So it's another big step forward that is coming in the next few years. And as we are now reaching the time that was allocated, and I'm certainly abused of your patience, I am finishing here my presentation for today, and I take questions if you have any. Thank you.
Thank you so much, Paolo, for the very nice presentation. It was very interesting, and yes, a lot of amazing things there. So I'll ask our participant if they do have some question to raise hand in the chat. Otherwise, I will go for some question in our social media. So the first question, it was, what is the difference between asteroid and near Earth objects, NEO? So what is the difference between asteroid and near Earth objects?
Okay. Okay, can you still hear me? Yes. Okay, so they are all asteroids. Broadly speaking, asteroids are all small objects that do not enter the category of planets, because basically they are small. They don't have a big gravitational influence on the other objects. They are mostly the largest of them are hundreds of kilometers in size. But then you have a category that comes closer to the Earth, and these are called near Earth. So basically, what you see here is all these color lines are asteroid orbits, and some of them are crossing the Earth orbit. It is white here, and those that crosses the Earth or that come very close to the orbit of the Earth are called NEAs, near Earth asteroids or near Earth objects. And these are most of them are just the largest population, let's say, is 1 kilometer, 10 kilometers, but most of them are much smaller than that.
Okay, the second question is how the orbit of asteroid can be calculated, how we measure them.
Oh, this is a very interesting question, because it's a whole, I would say, whole domain of study. It is basically it's a very, very fundamental problem of classical astronomy. So once you have let's say 3 observations of a position of an object, you can always compute by mathematical approaches. You can compute which is the trajectory of this body around the sun, and derive what is called a Keplerian orbit. So an ellipse or a circle-like trajectory around the sun that describe the orbit of this object. In practice, then things are much more subtle, because for instance, thanks to Gaia astrometry, to the position, very accurate positions given by Gaia, we detect in this trajectory perturbations by other large asteroids, or perturbations by the planets, or even the Yarkovsky effect. So the trajectory is no longer a simple ellipse, but is something that is described by more subtle effects, for which you need more accurate mathematical models. And in practice, what happens is that the observations are collected. So all these observations are positions of an object at different times. And then there are computer codes that are sometimes highly sophisticated, that takes all these positions together and are capable to compute the trajectory of the asteroid that fits these positions. I just add that this is done constantly. Minor Planet Center repeats, and as well as other centers such as JPL or others, they compute and update asteroid orbits, because each time that new observations arrive that are available by different telescopes on Earth, basically you have new data, so you have to update the orbit, and over time, and the more you accumulate observations, the better the orbit is determined.
Okay, and another question from Sir Naufal Bermauya. He say, if we are sure about that, the origin of life in Earth could be water from asteroid.
This is a good question, because not all the water the asteroid brings is probably sufficient to explain the whole water content on Earth. There are probably also comets that contributed, but the question is debated. And for sure, asteroids played a big role in bringing water to the Earth. Otherwise, we would not explain completely the composition and the amount of water that is present on Earth.
Another question from Bilal. He say, how much is the potential of collision between Earth and a dangerous asteroid?
How much is the potential? It depends. So I can show up again something on which I went rather quickly, if I find the slide again. Okay, so basically this is what you can call potential in terms of frequency, so how often a collision can occur, and how strong the collision can be. So this is expressed in megatons of TNT equivalent. So very strong explosions occur much more rarely. So this Chicxulub crater that created the Gulf of Mexico, basically, across Yucatan, is the one that was at a certain point suspected to be at the origin of the extinction of the dinosaurs, just to make it simple. Okay, so we go toward the frequency of once every several hundred millions of years. So these are the very rare events. And as you accept to go down to less energetic events, you go towards more and more frequent possible collisions, down to Hiroshima power equivalent explosion over several tens or years. But of course, these explosions occur mostly in the atmosphere. Sometimes they occur over the ocean or in areas that are not where there is nobody living on Earth, which is the majority of the surface. So you don't have a witness for this small end very often.
Another question from Sir Naufal Bermauya. He say, in how many years we can measure a asteroid when they just can hurt our Earth? How we can determine that?
Okay. Let's say, okay, let's make an example. I discover an asteroid today, and I find that it passes close to the orbit of the Earth. So this is the first condition. Okay, then I say, okay, now this guy is interesting. I want to know if it can impact the Earth. So when it crosses the orbit of the Earth, does it cross close enough first? And does it cross at the right time, when the orbit is at the crossing point, when the Earth is at the crossing point when the asteroid arrives? So these conditions must all be met for an impact to occur. And in order to know precisely if this is possible, then it becomes more tricky because you have to push the accuracy of your orbit determination to its limit. And there is an additional problem because if this object crosses the Earth and not far from the Earth, then it is very perturbed by the gravitational field of the Earth and its trajectory changes at that point. And after the change, it's very difficult to predict exactly how its orbit will be. Let's say the difficulty of predicting a future trajectory increases. So I would say that for an object that comes close to the Earth today, over the next few years, if it never comes close to another planet or to the Earth again, its orbit is predictable, so over a few years. But then if it has another close encounter, so it comes close without impacting, its orbit changes and it must be monitored to understand its trajectory, how it is going to change, and then to make another prediction for another few years. So it's a matter of continuous monitoring and improving over the years that gives you the most accurate predictions of when an impact could occur. And you understand the difficulty. If we discover an asteroid that is really on an impact trajectory, we want to be able to do this exercise quite fast. So there is a kind of contradiction in what we can do and what we should do, but that's life. We have to push our knowledge and our techniques to the limit to be able to do this exercise.
Another question from Esma. She followed us in the live in our social media. She say, what and how many technique and what tools we use to find and track asteroid?
Oh, the main techniques to find asteroids are the largest surveys, so large telescopes on the ground that can reach faint magnitudes, so they can reach faint objects to discover the smallest possible asteroids, because the big asteroids and the big near-Earth asteroids has already all been discovered. So we need to try to track to discover the smallest ones, which can for which the population is far from being complete. So this is done by, well, maybe I have a couple of slides on that. It's done by telescopes. I just choose here two examples of famous surveys. The telescope above is the Palm Stars in the Hawaii, and below you have the Catalina Sky surveys that produced many positions and discoveries. And here you can see, if I find it again, yeah, the increase of discovery of near-Earth asteroids over time. So you have in blue all the asteroids discovered, and in red the asteroids above 1 kilometer. So you can see that the red part is basically constant now, meaning that all asteroids larger than 1 kilometer or near Earth asteroids larger than 1 kilometer have been discovered. But if you go down to 140 meters, which is the orange part, you see we are still increasing. So we are missing many objects that are 100 meters, and not to speak of the smallest ones, which are below 100 meters, which populate the blue part, which is the increase is very steep, meaning that basically when you point a telescope which is powerful enough, you discover many of them. So the technique for discovery is always the same. Observe the sky with the cameras, take images, compare images to see if something is moving. And if something is moving, check the catalogs if this moving object is already corresponding to a known one or not. If it is new, raise your hand, send the observations to Minor Planet Center, say, hey, I discovered a new one, probably, please follow it up, and so on.
Thank you, Paolo. Another question from Salma Sila here with us in the Zoom meeting. She said, for the asteroid hitting the Earth, can we predict their periodicity about their size?
Oh, the answer is quite simple. If you look at the at the dust coming from of cometary origin that creates the meteor streams that we observe during this, preferentially over the year in specific periods. So these are periodic in the sense that they recur every year about the same epoch, because that's the time when we cross the trajectory of the comet. But if you talk about asteroids in general, and all the small objects that come from the near Earth population, they are not periodic in general, because it's simply matter by chance, a very chaotic mixing mechanism that injects these objects on a large variety of objects, of orbits, and that can then impact the Earth or not anytime. All we can probably try to study today is not if there are periodicity, but if in the past the impact rate was different statistically, and how much larger it was, and so on. So the trend over large period of times. But we don't expect to see any strong periodicity unless, but this is not so clear yet, unless there are some asteroids that are releasing particles such as Bennu or Phaethon. But again, these give rise to meteor streams that we observe at specific nights over the year, and is not exactly a periodicity of a big, let's say, hazard, dangerous events.
Mm-hmm. Okay, fellow Nidai asked the question, what is the asteroid origin?
Okay, so I mentioned at the beginning the fact that what we think is that they originated as leftovers of the formation of the solar system. So this is very roughly speaking what we can say. And then by looking at the point in more detail, we saw that they originated probably in many places in the solar system, where they remained, let's say, as fragments that were not accreted by the largest planets. So these fragments were gradually cleaned up by the fact that the largest planets were accumulating material, so there were, or even cleaned up by the fact that the largest planets perturbed their orbits and threw them away from the solar system. But those that remained after all the chaotic phases of the solar system rearrangement are now in places where they are stable enough to stay there for a long time, because our solar system is now pretty stable. And so we observe what remains of all this complex mechanism of mixing, and from the early phases where they were left aside from the formation of the large planets.
Another question, Paolo, from Zainab. She say, can planetary radar be used to reach and detect asteroid?
Radar?
Yeah.
Yes, they can be used and are used. The point is that the radar signal becomes very weak when you go far away in space. It's like the fourth power of the distance. So you really need to use big radars. I have here a couple of slides on that. Big radars like Arecibo, for instance, which is built in a valley, and it's very large surface, a very large power. In order to reach the asteroids, you really need very big power of the signal. So this is a technique is mostly reserved to near-Earth asteroids, because they can send back a powerful enough signal to be detected and measured. And sometimes it has been used for the largest main belt because they are large enough to send back a signal. But it's not possible to study by this technique asteroids that are both far and small at the same time.
How are human accessible asteroids identified?
What do you mean by accessible?
I don't know, it was written like that.
Accessible in terms of space missions, maybe?
Yeah, I think so, because as she wrote it like that, she say, how are human accessible asteroids identified?
Human accessible, okay. Let's say what is accessible by a space mission in general, because then if you can put a human on the space mission, it means it is accessible. In general, what happens is that they are selected on the basis of two criteria. First one, the asteroid must be scientifically interesting, so we must think that it brings some useful information to understand the solar system in its evolution. Second point is that it is not far from the Earth in a dynamical sense, in the sense that you require not too much energy, too much fuel to go from the orbit of the Earth to the orbit of the asteroid. In some sense, it means that the velocity of the object is not as far from the velocity of the Earth, roughly speaking. So it means that basically you need to accelerate your spacecraft in such a way that you have enough fuel to do that. It's much more difficult to build a mission that goes far away to an asteroid that has a very strange orbit. You need to target asteroids that are close and that you can reach with without consuming too much fuel. Otherwise, you have to build a very expensive space mission. Now, this is in terms of general accessibility. To send a human to an asteroid is still another story, because this enters into the domain of all the difficulties that we have with human space flight, which becomes very difficult when you go far from the Earth, and it takes a very long time, which has not been experienced by human people in space up to now. So this is not no more a problem of selecting an asteroid, but to know how put a human on a spacecraft and do that.
And the last two question is first one from Salma. She say sometime asteroid would change trajectory. Can you give an explanation for this phenomena? And the second question is from Maya. She said, can asteroid type determine the degree of dangerousity of the asteroid?
Asteroid type?
Like type M, S, or C.
So first, how do they change trajectory? Basically, they change trajectory because they are gravitationally perturbed, because there is a planet that can induce a perturbation on them. Now, I mentioned before, the asteroids that come close to the Earth or to the terrestrial planet, they change trajectory because they come in the gravitational domain of these planets very close, so that their trajectory changes dramatically. The other mechanism is very, very more subtle changes, meaning that if I find the picture again, I showed you the existence of resonant areas in the main belt. So here it was. Yeah, you can see these black gaps where you have no objects at certain distances. This is because each time when an asteroid is at those distances, each time he makes a revolution around the sun, one complete orbit, one planet makes a number of revolution too, which is an integer of a multiple or of the revolution of the asteroid. So for instance, you can have resonances that correspond which is called 3-to-1. So when an asteroid makes 3 orbits, Jupiter makes 1 orbit, and it becomes an accumulation of resonating perturbations that are very, very small each time, but as they happen always in the same positions, they accumulate their effect and they displace the orbit of the asteroid this way. Then the other mechanism I illustrated was the Yarkovsky effect, which is thermal recoil effect, so thermal radiation that is very, very subtle push. So this moves the orbit of the asteroid by only 1 to 10 meters per year, but over hundreds of thousands of years, you can see the effect of that. The other question was about the asteroid type. Yes, if you have an iron meteorite and you know from observation that the object is compact as an iron meteorite because it's made of iron, of course, it has much greater chance to impact the Earth, impact the ground, than an asteroid that is very fluffy, that corresponds to an object that is maybe with a very, very poor cohesion, or comet-like, made by a lot of ice, and can maybe completely being destroyed during the entrance in the atmosphere. In that case, you can predict, and it's very important to know this to predict which damage could occur. Now, what we are also studying are strategies to mitigate impact. So if we discover something that is in impact with the Earth, what we can do in advance, and also for mitigation, knowing the composition of the object is very important. To know, for instance, how it would react if you try to expose it, the kind of result you obtain is very different if the asteroid is compact or not.
Okay, Vali, and the last question from Paolo, he say, how can we recognize an asteroid?
In the sky, only by its motion. There is nothing that tells you in an image that given point of light is an asteroid. The only thing that you can use is to observe it at different epoch in time. So for instance, you take a picture of a given region of the sky, you take a picture of the same region 1 hour later, and you see that some dots in the picture have moved. And those dots are certainly, with respect to the stars, those dots are certainly objects are very close, so that are asteroids.
I don't know if someone else have a question. I think that we are done here in the chat and also on the social media. So I would like to thank everyone for the presence. It was a very nice talk. And thank you, Paolo, so much for the amazing and interesting talk. And it was really nice to welcome you today in AstroTalk project, which is project supported by the IAU and also different and several astronomical club association and institute in Tunisia. So thank you, Paolo, for the nice talk. And also I would like to thank our participant here from Tunis Science City, from Palace of Science of Monastir, and also Selma, and everyone is there with us here. Jorge, also from South America. Thank you, everyone, for your presence. Thank you, Paolo, for a nice and amazing and interesting presentation. And I hope to see you in another talk in the future. Thank you, everyone, and see you the next time.
Thank you, Maisa. Thank you, everybody, for listening and for attending. Thank you for your presence.
Bye-bye, all. Bye-bye. Ciao.
Ciao.